Okay, hello and welcome to today's lecture. It is Math 1B. We're going to start chapter 5. We had some questions about the course. First of all, I'm going to record the lecture. I'm going to upload them on YouTube and post them on Canvas for you. Homework and quiz are due on Sunday. And we're going to use Canvas to post the solutions. And Piazza is for discussion. So lecture notes are posted on Canvas. We're going to start on 5.1. So on page 1 and page 2 of 5.1, you can see the important definitions and formulas, how to find a limit of functions. On page 3, we're going to officially talk about integral. Very well. So what is integral? Where did it come from? Let us go over one quick example. Suppose you have this object in xy plane, x-axis, y-axis. This is your object, two-dimensional object. Suppose the length is, let's say, L, and the width is W. The question says, what is the area of this object? How do we find the area of this rectangular shape? What is the area? So, of course, it's just an algebraic object. You already know how to find the area of rectangle. It is area equals to length times the width. You calculate, you measure the length, you measure the width, you multiply them together, and you have your area. What if I give you a more complicated shape, a more complicated object? We can look at another example. Suppose you have a triangle, x-axis and y-axis. Well, the base is measured at B, and suppose the height is also given on y-axis, which is h. What is this area? How do you find the area? As long as you have your base and you have your height, the area is easy. Area is equal to a half base times height. Well, what if we have more complicated objects? So I expect you to ask, Professor, what if I have this object here, x-axis, y-axis, and my shape is like this? I want to have my function y equals to x squared, y equals to x squared, and I want to find the area between this function and x-axis, and suppose it stops here. So what is this area? How to calculate this shaded region below y equals x squared and x-axis? How do I calculate that? So asking questions about the area between different functions, x-axis, y-axis, x equals to a, x equals to b, raise the question of what's the efficient way to find the area? In two-dimensional space, we're talking about the area. In three-dimensional space, we're talking about the volume. This is the topic that you're going to learn in multivariable calculus. So to answer these types of questions, we come up with idea of integrals. We need integrals to answer these questions. Okay, let's see how we can define integral and actually find the area. How to define integral. How does integral work? So mathematicians used to have this method, which we call using riemann sum to find the area. How does it work? So let's get back to our previous example, x-axis, y-axis. So what do we have here? We have function, y equals to x squared. This is my function. And suppose I want to find the area between the graph of the function and x-axis, and x stops at 1. So this is the area that I want to find. This is my area. Let me shade this for you. What is this area? How to measure or calculate this area? So what we can do, we can take this horizontal measurement, this horizontal piece, 0 to 1, and start dividing this guy into smaller equal width subintervals. Okay, this is my graph. Y equals to x squared, so this is my y. And this is my shaded region, which is this guy here, and I want to find the area. Well, you might say, okay, suppose I want to divide this into 4 equal subintervals. 4 subintervals. Okay, I'm going to divide this by 2, so this is a half. Then I'm going to find the midpoint here and here, so I get a 4. And the next one is 3/4. Well, why I'm doing this? If I can divide this shaded region into smaller pieces, smaller rectangles, then I can find the area of those rectangles and add them all together to get the area, an approximation of the area of this shape. So, take a look at this. This little piece here has length, which is a fourth. I can find the measurement here using my function and actually form a very small rectangle, find the area. I can form another rectangle here, find the area of this rectangle. So this is the first rectangle, this is the second rectangle, this is the third rectangle. And use these areas to get a sense of the area of this object here. Okay, perfect. So let us call this guy S1 for the first area, S1 for the first area. This is my S2, S sub 2, the second area. Then I have my S sub 3, the third area, and S sub 4, the fourth area. So this is my S sub 4, and this is my S sub 3. So how do you calculate S sub 1? What is S sub 1? S sub 1 is the area of this small rectangle here. So what is the length? What is the width? The length is easy, 0 to a fourth. So the measurement here is just 1/4. This guy is 1/4. But how do you calculate this width? What is this? To calculate the width, we're going to use our function, which is y equals to x squared. So this point is actually on the graph of the function. When my x is a 4, my y value is a 4 squared, which is 1/60. So 0 to 1/4 gives you the measurement, the line segment measurement, which is a 4. To find this measurement here, this side here, we're going to use our function y equals to x squared, and this is 1/4 squared, which is 1/60. So what is the area? Length times width gives you the first area. So S1 is equal to a 4 times 1/60, 1/64. This little area here is 1/64. Well, we have to continue this process, find the rest of these areas, and add them all together to get an approximation of the area below the graph. Very well. So we found that little area here, the first area, which is equal to 1/4 times 1/60, or 1/60. This is your first area here. For the second area, you have to do the exact same thing. The area S sub 2. To find this area, again, we have a little piece of a rectangular shape. Here S sub 2. So I know that it starts at a fourth and it stops at a half. So it makes it easy for me to find this measurement here. A half minus a fourth. A half minus a fourth. This is 2 over 4. Which gives you 2 minus 1 divided by 4 or a fourth. This measurement is again a fourth. This length. So I'm good with my length. What about my width? So this point is 1 over 2. This is your x value. What is my y value? My y is, take your x and raise it to 2. A half raised to 2, which is 1 over 4. So this little area here is a 4 times a 4, which is 1 over 16. S sub 2 is a 4 times a 4, which is 1 over 16. Okay, I found the second area as well. I continue the same process, the same logic to find the area of S sub 3 and S sub 4. For S sub 3, I have another rectangle here, and I know that it starts at a half and stops at 3/4. A half, 3/4. Okay, to find this measurement here is just 3/4 minus a half, which is 3/4 minus 2/4 or a 4. We expect that. Why is that? Because we say that, hey, I'm dividing this interval 0 to 1 into 4 equally distance, equally measured subintervals. So when this guy has measured a 4, this is a 4, this is a 4, this is a 4 as well. So my horizontal measurement is just, but for my vertical measurement, now I'm working with this point here. I take x equals to 3 over 4. I'm using my y equals to x squared to find this length here. So I have 3/4 raised to 2, 9 over 16. So this guy is 9 over 16. And the area is 9 over 16 times a 4. So S sub 3. Okay. S sub 3 is equal to a 4 times 9 over 16 or 9 over 60. And finally, for the last piece, S sub 4. I know that my horizontal measurement is just a 4. So this is a 4. 3 over 4 to 1. 1 minus 3/4. You already know that this is 1/4. And for the width, I'm going to use 1 and type that in because this is the point on y equals to x squared. So 1 squared is 1. So the last area is equal to 1 times a 4 or 1 over 4. Okay, so we found these little areas, 4 areas. And we say that, well, if I add these areas together, S sub 1 plus S sub 2 plus S sub 3 plus S sub 4, it gives the area which is a little bit larger than the area that I'm expecting. it's an upper approximation. So this is equal to 1 over 64 plus this guy is 1 over 16 plus this guy is 9 over 64, and finally I have 1 over 4. So this is 1 over 16, 64 plus 4 over 64 plus 36, which is 9 over 64. I'm going to have to take it differently, and I have 16 over 64. So if I add all of these together, I get 25, 29, 30 divided by 64. So this is the area of the sum of all of these rectangles. But my goal is to find the area of this shaded region below the graph of the function. As you can see, I have some areas that are above the graph of the function. So this is just give me an upper approximation. You could say that, okay, instead of taking these rectangles, I'm going to form these rectangles. So take a look at this. This is my just subintervals, 0, 1, and this is my shape. It's going to be here. Okay, so it touches x-axis at 0 and 0, because if you plug in 0, you get 0 back. Very well. So I have a 4 here. I have a half here. I have 3/4, which is here. And finally, I have 1. So I say that on the first subinterval, I'm going to form the rectangle with length of 4 and height 0. If I plug in 0 into y equals x squared, I get this flat rectangle. For the second one, instead of taking a half, I'm going to take a 4. So I'm starting from lower limits of each of these subintervals. Okay, this is another rectangle for you. Then here you have the third rectangle, and finally you get your fourth rectangle. So this is your S sub 1. This is your S sub 2. Then here you have S sub 3. And you have S sub 4, the fourth area. If I find these areas and add them all together, it gives me area which is less than the actual area of this object. Okay. With the same logic, we're going to calculate S1, S2, S3, and S4. For S1, it's obvious that the length here is a 4, but the width is 0, so you get 0 plus. The length is a 4, and the width is actually a 4 raised to 2 plus S3. The length is a 4, and your width is equal to a half squared. And plus, finally, the area of the last rectangle here is a 4 times 3 over 4 raised to the second power. Okay, let's calculate this. 0 plus 1 over 64 plus 1 over 16 plus 9 over 64. If we take common denominator between these, you get 64. Here you have 1 plus 4 plus 9, which gives you 14 divided by 60. Again, our goal is to find this area. By taking upper limits, we have an area which is larger than the actual area. By taking lower limits, we find an area which is smaller than the actual area. But what is our conclusion? Our conclusion is that the area of our object, the actual area, is a number between these two, 14 over 64 and 30 over 64. We're sure about this, but our question is, what is the actual area? So these are the methods that mathematicians used to apply when they didn't have the shortcuts, the nice techniques that we have in this class. So it was just an introduction how to actually approximate the area of any two-dimensional object. So what if instead of having just 4 subintervals, we get n subintervals, infinity subintervals, to get a better approximation of the area of our object. So in general, what are we going to do? We're going to take any random object, two-dimensional object, like this, x-axis, y-axis. By the way, we are on page 4. Suppose you have this area here between the graph of the function. Okay. And let us just divide this into very small subintervals. So we get these strips. We take each of these areas, S1. So this is your S1. This is the second area, S2. You have a lot of these little areas, S2, then S3, S3, S4, S5, S6, and Sn eventually. So these are all small areas of these small rectangles. So suppose this is S sub n, and before S sub n you have S sub n minus 1. So let's have this right here. S sub n minus 1. If you add them all together, you get the best approximation of the area of this two-dimensional object down here. So the notation. Definition. Definition. The area of a region, like A, let's call it S, that lies below the graph of function like f. So suppose this is your function f is